the slides. So here are the slides for the last session of the day. So in the previous examples, I spoke about a bit about machine learning and all the advantages of machine learning and disadvantages. And I also showed you these examples with how you can use just buffer distances to make spatial interpolations. There is one more technique, as I said, similar to this buffer distances, is to use distances to, let me see, I think I have now two same sessions. Yeah, I don't need two. So there's a different option is to use the distances to the nearest neighbor. That's the method from the Matter package, developed by Sekulic et al. And it's very intelligent because you basically you take for the distances you calculate the distances to the second neighbor, first neighbor, second neighbor, up to the 10th neighbor. So here I can specify the neighbor observation up to 10th neighbor. And then you see the algorithm also computes so distances to the 10th neighbor, and it computes also the values. And how do the values look like? It's something like a Voronoi polygons. You get something like this. Basically, it's kind of a splits the values, decides areas, splits the values based on the proximity. Okay, so and then you do again overlay. You train a model. And you do combine these things, and then you have a model looks like this. Basically, zinc is a function of distance to first neighbor, second neighbor, and also function of values from the first neighbor, second neighbor, etc. So there are two types of covariance, not just geographical, but also the values. And when you fit the model, you can see it also gets about 0.46, so it's a bit less than what you got with buffer distances, but you have less, you have only 20 layers, you don't have 155, so you have 20 layers, and when you produce the predictions, you get something like this. So it's a bit different pattern, and we can look at that in Google Earth, and let me see if I have enough RAM, yes. So let's take a look at that in Google Earth. So there's this one. And so we can compare the two predictions by two different algorithms using basically points. And so this is this one with the distances. That's kind of like it will be lots of these pixels going up and down. So so that's a bit maybe strange pattern. Maybe it's because of the size of these data sets also. Maybe it's just because we use only 10 distances. We could use distance to 20 points, you know. But it's a bit different than what we get here with this one. So this one is a much smoother, right? So it's a bit it becomes a bit different. So which one is better? I don't know. Difficult to say. You could do cross-validation, and looks like here the extrapolation part, it's very different from the two methods, as you see. This is where the real differences kick in. So you can see where the differences. But definitely you could use that method. So that's something we spoke. And then other thing we spoke about is the modeling seasonality. So that's something that we're going to implement it. So now it's not just, hey, this is the theory, but now this is, I show you that function in practice, and we compute for every pixel. And it's not complicated, it's not very computational, so we can compute it for whole world, many rasters, you know. So yes, this session we will talk about ensemble machine learning. I also showed you ensemble machine learning. I see it as a remedy to prevent from overfitting and also to prevent from extrapolation problems. So there's a good reasons to use machine learning, but it increases computational complexity, and definitely if you're not prone to making more code and computing more, then it's not a direction for you. But if you feel like, okay, I do more computing And as I told you, computers get you know, exponentially more efficient in computing, and I don't know in a couple of years what will be computational efficiency, but now maybe some code that it looks very computational, in 2 years you run it in a few seconds. Maybe not in 2 years, but maybe in 10 years. So that's a question. So what we're going to look at now, Ensemble Machine Learning, we look at the MLR package. There's also Superrunner package. Also, there's a tutorial that explains how to do it. I'm not going to run that as a demo, but just be aware there's many ways you can do Ensemble. Not too many, but let's say there's about 3 or 4 frameworks in R, from H2O to Superrunner to MLR, MLR3. So there are a couple of frameworks, and you can apply Ensemble Machine Learning. And then I will show you this with the 3 data sets, and I will pass the last data set, I'll pass to my colleague, Carmelo, and he will actually show you the real data and really big data. So we look at the, actually, I should show you here, we look at the whole Europe training points for Fagus Latica. And you can see that's a large data set even to visualize. I mean, when I open in QGIS, it will take some time. And even it's difficult to see which are the points, which are occurrences, and so there's zeros and ones where the point comes and where the species comes and doesn't. So it's a really real data set. So we'll show you that in practice. So that's the plan for this third block. So 3 case studies, and we'll do step by step. First, a bit of introduction. Why ensemble important? So we can potentially increase accuracy. That's a first reason why people do ensembles. But it's not a lot. There's no ensemble. There's many magic. There's no magic behind ensemble. So if you do ensembling, you will see there's a really gentle increase in accuracy. So there's never like I double the accuracy or something. That will be very strange, because that means that some of the learners is really polluting the model. But let's say if you have really stable and reliable learners, then there's just a gentle increase in accuracy, usually. It also helps with the extrapolation problems. There's a much more training, so you do maybe 10 times more training than if you just use a single model. And you can see, you can derive this, what they call a model-free prediction errors. So the prediction errors which are not dependent on the model. So that's prediction errors independent of the model, and you can call them model-free. And also there's in MLR, you will see some, in some sections you can combine, where you prepare the data, you can combine the model selection, feature selection, fine-tuning, you put it all in at once. So you just say, I want an ensemble with all the other stuff done. And that's also nice. So you don't have to separate it, you integrate all the things. Yes? No, I will show you there's a different ways to do the ensemble, different approaches. And we often use this algorithm called Superrunner, which is based on stacking. And stacking means you create a meta learner. So since you're asking, I can show it. So it has kind of 2 levels. It's a 2-level modeling. In the first level, you do k-fold. You do k-fold to fit all these models separate. So let's say here there are 4 learners. You see 4 learners. Then you take this and you do second-level modeling. And this here you predict the so-called meta learner. And this meta learner basically then shows you the final model as a function of individual models. So it's a model of the model. Yeah, and sorry, this is a bit complex, but in principle, I can show you here. This has been worked out in this example. I just have to run. Let's see. I had to restart the machine, but not a problem. I just have to rerun up to this plot. Well, actually, it did save. So here, when I do this ensemble model, you see, I get now I change the model, but I get the final model is a function of reg GLM, GAMBoost, and NNet. Yes, and this is kind of weighted average when you think about this, because when I use a linear model, then to predict the final value, it's a weighted average out of, and so basically what it means, it's very simple, the coefficients of the weights. If you have a weight 0.09, you could remove that learner. There's no point to keep it. You just compute inefficiently. So that means I will go and replace that and put some other learner, maybe change it, right? So I said, okay, this one doesn't work. CV, maybe this one, and then I rerun it, rerun this one. Let's see if it changes anything. So here we get, let's see what happens. So this one I actually cannot fit, because for this CV GLMNet, I need to have at least 2 covariates. So this one doesn't work. So I will have to put something else. Let me put again Ranger, see if that changes anything. Every time you run, because it's a random subset in the training, unless you put the seed number, it's a random subset, and every time you get different coefficients. So don't get confused with that. So here I do get a model, and the model says, again, random forest, no point to use it. It just doesn't help. Just the GAMBoost and GLM. Okay, I would still use it, you know, but have in mind that then the uncertainty will be high. So when we plot compute and plot the uncertainty, it will look something like this. So now this is a different one. So the uncertainty goes high because I kind of force the random forest, and then the uncertainty of that random forest propagates to the ensemble uncertainty. I think that's probably that's more, again, more realistic, you know, to do this than to only pick up the learners that match the data, because you could do overfitting. Yeah. So, but officially, when you look at the individual model, this model, I mean, there's no need to use Ranger, random forest. It's a very low coefficient, very low weight, and also this coefficient is not significant. This 3 stars and means significant to the level 0.01, so 0.1%, and then two I think are 0.5%, 0.5%, yeah, and then 1 star. I'm not sure 1 star, but so these are different significant levels. Okay, so that's about that. We look further. So that's this meta learner. This is this Superrunner. It's explained. Colleagues from California, they worked this out, and I think they published on. This person did a PhD on this topic, and then this is when they applied. They prove it. You know, we repeated many times. These are many repetitions, right? All the dots are individual repetitions, and you can see if they really are the Superrunner. It has accuracy. It's always a bit better. Not always. I'm wrong. Sometimes it can be, Superrunner can be equally bad as the best learner. But officially, they should never be significantly worse than the best learner. That means something's wrong. Just when you think about this. I mean, if you already have the best learner, you cannot degrade the predictions, right? If you do everything properly, I mean. So, but if you do everything properly and you pick up the subset of learners, then there's a good chance that the ensemble learner, super learner, will be slightly better. Okay, so then this shows you for this mass data set. These are different models I use with the subsetting, with the 5-fold. And each fold is the J. J is the fold, right? And so you can see that predictions can be quite different. Yes, you see that? There are quite oscillations in predictions. It's the same inputs, it's just different model. And then this one is the weighted average through meta learner. And so then you can see that it kind of takes the best out of multiple learners. And then you can estimate this model error also. And you see the model errors, they're high where you have high values. So they always be proportional to the values. But also the biggest, we have this isolated point with a one high value. If I look at the predictions, I have here one high point. Suddenly there's just a 1 point, very high value. And so every time you have a 1 point in space that's isolated, for sure it's going to, unless it's really correlated with some covariate, but it's going to usually be high error. Okay? Usually it's going to be okay, because it could be if it's taken out. Imagine you do 5-fold, and in this 5-fold, maybe 2 times it will be taken out, and 3 times will be stayed in. And then these 2 times that you predict without it, the model will say, oh, wow, I predict much less. And then you have the high error. Yes, and but otherwise, if you have where you have high values, you also get high errors. But that's logic of the high values, just because if you look at it, I mean, obviously where you have a much higher values, if you have skewed distribution, the errors are proportionally bigger. So that's this Superrunner, and you see we use the software to do this, to do the ensembling. So if you look at these steps, the steps are like really straightforward. I mean, you define you say, this is my target learners. I can now turn this off. I can turn this off and put the old one. So I said, these are my target learners. This is just to define them. And then I define the task. And you see, this is a regression task. And if I type in the task, it will show me something like this. Let's see. So it shows me the definition of the task. It says it's a regression task. I have 100 points. I don't have any blocking. I don't have coordinates, and there's no missing values. Okay. So and I have only one numeric covariate. I don't have any features, ordered values, whatever. So it's a simple model. And then once I define the task, then I can specify the stack learner. So if I press the first one, so I get, again, this is just definition. There's no computing. It's just a definition. So I define a learner, which is called a stack learner, which basically I define this meta learner. And I say the meta learner, where is it? It's a regression, but doesn't say what is the meta learner. It's in the definition only. But I can put some hyperparameters, etc. So this is just a definition. And then when I do the train is like from Caret, from all the packages they use that train. When I do train, then it does the computing. And if you look at it, it can be a bit computationally intensive. Let me see. Now it's a very small data set, but let me see if I put this on. So we will track that. At the moment is nothing, computing nothing, but it can be later on, we'll say it can get computationally intensive. Sometimes you have to wait 5-6 seconds, But otherwise, to run the whole script, the all R Markdown, I put a couple of data sets because I want to give you an idea about spatiotemporal regression. So I put relatively larger size, and it does take about 10 seconds, depending how many threads you have. But it takes 10 seconds to train. And it's good that you get an idea that it's very computational, right? So that's about MLR. I have a contact with people from MLR, and they're very helpful. Yes? Yes, I just wanted to show you 59. Yes. No, computationally you waste money. If I take 59, you waste resources. So instead you start with 59 and then basically get 5. Yes, so I think from this 59, about 50 are the legacy models, and about 5 or 6 they're interesting. They're interesting because they are cutting edge. Right. If you have time, yes. If you have time. If you don't have time, they suggest, because if you have 100 data sets, and he's one of the developers, MLR, it's great to be lupus in fabula. So if you will take all 59, if you pick up, let's say, 100 data sets in R with multivariate data sets, in this 100, you will get, in about 98, you will get always the same. So there's no need that you have to redo that. So many are legacy learners. But I would use some GLM, just to protect. You see this overfitting. So, and I show you with a synthetic example. If you put one more legacy like a GLM or CV GLM net, then you protect from overfitting. If you have a simple structure, let's say there is a potentially simple structure, linear structure, then the other ones, they will do damage. And some are very computational, the support vector machines, they exponentially with the number of covariates. And you start going like, I cannot use this. I mean, it becomes so computational that we cannot use it for any project. We could use it only really for small data sets. And then some we don't use based on experience because they're just so computational. So we the ones I gave you in the script, these are the ones we use for many projects. So this is these ones here. The random forest GLM or CV GLM net, Gamboost, and support vector machines. You could also add maybe some others, and the new MLR3 will have more models, but otherwise there's no need to do all 59. This is this make stack learner, so that's the definition. In this definition, you will see I can do different things. Let me open that. Help. So you see, you can do different type of methods for stacking. I usually use the stack CV, but and this is computational. But if you want to speed up, I think hill climb is faster. And when you do the stack CV, then you can do also resampling method, which is like usually it's a 5-fold cross-validation with refitting, but you can also put a blocking parameter, and which is very important. I will show you that in the example. It's important to block to avoid overfitting, especially with the space-time data where you have station data. They're very important. And this is, I had to learn this basically hard way by, overfitting and then looking, oh, it's great, R-square. And we almost submitted the paper published, and then we took the whole stations out, and the R-square was about 40% less. And then we said, oh, what happened here? Well, we overfitted. So that's another important thing. There is also Superrunner package, but as Patrick also told me, it's not really maintained. It's really worked out. It's really great text, and I use it for some data sets. It works very similar to MLR. It also does stacking, and it has also cross-validation separate just to do accuracy, so without fitting a model. So that's, but it's not so well maintained, and there was just 1 or 2 people made it. And then I made a package land map, and this land map package, it's Deus ex machina. So it wraps up my knowledge and it puts it in a one line, and you say, here are my points, here are my rasters, make spatial ensemble machine learning, also fit variogram, everything. And you just go through all the steps in one line, and you just get it, and you can make predictions. And you can predict classes, numeric, whatever, and you get the uncertainty, everything, and you can plot directly. So that's the Deus ex machina. But be careful if you have wrong assumptions or data set which is clustered, then I cannot help you. It's not, it's this, the methods to deal with clustering are not implemented in PlanMap at the moment. I only do spatial cross-validation. So this is the reasons to do ensembling. Kind of already said that. What else is important? If you put this in open knowledge maps, you can see what people publish on Ensemble machine learning. Do you know these open knowledge maps? You put a term and it will show you publications clustered. It will do automated clustering and put the publications that are related. And also you can see which are the subfields. So that's a nice way to organize data. Sorry, the publications. Okay, now we go to the real data. There was a lot of introduction, maybe long introduction, but I needed to do that because I'm not going to now explain you the seasonality, modeling, blah, blah. So I go straight to the modeling, so space-time machine learning. And this is the data set we published 2012. As I said, we did a space-time regression kriging or universal kriging, and we got that predictions I showed you. And the space-time data looks like this. So these are the actual 3 stations, and you see daily measurements. They can go up and down. It's kind of like a bandwidth of the oscillations between days, as you see. And you can see if you're in the mountains or if you're in the plain or next to the coastline, you can have different peaks, and also they happen at different times. This black line is just a spline fitted to that, so it's just a spline. There's no like nothing special. So let me look at this data set in R, if you can still follow me. So that's here. So that's this data set. And I load it now, it's on my disk, it's on the disk, so I load it locally. It's not in a package yet. And this is a typical, let's say, typical meteo station data set. You have the meteo data, which you have the ID of a station. Then you have the date, and you have mean daily temperature, MD temp. Yes, and then the C day is the cumulative day of the year, starting from 1970. Okay, so that's a typical data set. It has almost 45,000 measurements of temperatures, and then we have another data frame, which is the station locations. So we have the ID and X and Y. Okay. So that's what we start. So these are the training points. Now we load the covariates. Covariates, we have 2 sets of covariates. One are the static covariates, and one are the dynamic covariates. Okay. For example, elevation, distance to the sea. These are the basically static covariates. They don't change through time. Here's the map of the elevations. Nothing special. It's just a map of elevations for the whole block. This is Croatia here, Balkans, whatever. And you see, this is just the elevation. You can plot something like this in Netherlands, but you have to increase the colors, the range. You decrease the range, of course, and you lose more drastic colors. So these are the static, and then for each pixel, I have also latitude, longitude. The map is actually in the projected coordinates, but I also put latitude, longitude for every pixel. I could plot that also. So that's, for example, 4. You see that it will be a bit curved, not too much, but it's a bit curved. You see, it's a bit like, so it's a really sphere geometry, right? You see it on the image, yeah. So that's the latitude, longitude. So this is static. And now we have dynamic. And dynamic, there's a lot of data, so you can play with it. But we have in a folder, we have a 45, let me see, 46 images. And they will be in this folder under the ODS workshop, R training, input. And then you have a folder. And this one has all these GeoTIFFs. This in our real projects, these are also like this, but there will be 10 terabytes. Yes, so there's lots of GeoTIFFs. And I don't have to read that data. I don't have to read it in R. I don't have to load it in R. It's inefficient. I will just read and if it's a larger data, I run out of RAM and you finished. So what I do, I first overlay the static data. I just do overlay. So now I have station ID, so 152 stations. So I know what are the values of the static covariates. And then I do a space-time overlay. And this is something I said we're going to use the Terra package because it's very fast. And I will load this little function I made through sourcing the code. And I will copy. So I copy to this data set, I copy the XY coordinates. And also I will put a row ID so I don't make a mistake. And I convert this date, the row date, I convert it to the SDate format. And now I have to do something. I have to strip. So if I look at the list of the GeoTIFFs we made, list of GeoTIFFs we have, sorry here. So I have the list, LST list day. I can see that in the name of the file, you see in the name of the file, I have the date. I have the 2006 0101. Yes, but I now have to strip the date because I have to estimate. I know this is an 8-day data set. MODIS NDVI, it's an 8-day data set. We can also look at it in a QGIS. And now I strip the name and I take 4 days for the start of the MODIS time reference. I take 4 days minus and I add plus 4 days for the end. And that's why I make it an 8-day. Okay. And so this is why I strip this and I convert that to the list of dates. So if I look at the first date, let me open it. I already prepared it so we don't lose time. But here's the MODIS. Here's one MODIS image. This is the one-to-one. That's what you download from the MODIS website. And you see there's quite some problems. There's missing pixels, right? There's missing pixels. There can be some artifacts. Let me see somewhere. There seem to be some artifacts because of clouds, like here. So it's not a perfect data set, but it's one of the best data sets to model daily temperature. Okay, so it has problems, but we want to use it. And it's, as I said, we have 48 in time series 1 year, 2006, we have 48. And now we created this begin end time. So let's take a look at that. If I take first 5. So we see these are the dates. So this first one starts on the 28th of December 2005. So actually it goes back. And then the end time, it's just the same thing. It's just basically the 4 days added. So this will be 5th. Yes. Okay. So I defined this thing I was sketching. I defined the begin and end time for every GeoTIFF. And now I do the overlay. And I do it in parallel. And as I said, this function is generic. You can use it with any data set. And just to show you, so here I do the parallelization and I say run separately for each GeoTIFF. So for each GeoTIFF, it will run. So if I have 46 GeoTIFFs and I have 46 threads, it will run them at the same time. Okay, so you can do overlay at the same time and it speeds up drastically. But I only have 6. So I can run that in parallel. So let me do that. I will run it from here, the whole thing. And I will open my here, and you see it's running in parallel. It went fast. It's not so many points, 155 points, but it takes literally takes like 2-3 seconds. And this way I did a space-time. And what you get as a space-time overlay, you get values in the long format. Do you know this long and wide format? Long format, it means I have each space-time ID space-time ID, I get value of the temperature. So instead of having like, if I did just a spatial overlay, then I will get 46 images. And then I have to rename the blah, blah. I just get one long format. So I get 44,000, exactly the same as the space-time matrix. I get 44,895 values. And you see there are zeros here. And these zeros, this is not good because these zeros are missing values. These zeros are here, unfortunately, they're the missing values. So here is no data, but these are the missing values. And so that's something we have to be careful not to use the zeros because these are not actually zeros. These are missing values. Then I repeat it for the nighttime. Do the same thing for the nighttime. Again, watch it in parallel. And then I merge. And now we have two data sets. And now we can do a join all in dplyr. So we join the meteorological station data, the results of the overlay. Yes, and we join that, and then we just add the static data, and off we go. We have now space-time matrix, but we also want to add this geometric temperature. Remember, we computed it, so we add extra column, which is the daily geometric temperature. This is just computed from the latitude. We have the latitude column, and we have elevation. So elevation, you have the day of the year, and you have the latitude, and we compute this thing. And so now we have everything, and this is a complete regression, space-time regression matrix. And now we say mean daily temperature is a function of the geometric temperature of the MODIS daytime, nighttime, and distance to the sea. Distance to the sea is the same every day, right? It's the same. So this is a static covariate. So we have a mixture of geometric covariate, dynamic, and remote sensing-based dynamic covariates. And then I do the same, it's the same code, nothing changes, except I will now run a ranger in parallel, and I want to get importance. So now I modify this a bit, and I say, make a ranger that also does a bit extra things. And so we define the task, and then we can do the model. But because this model, we have the station data. We have to use the blocking. So we block stations. So we put this blocking parameter. See here it says blocking true. So we have the whole stations. We take them either out of the modeling or in the modeling. So we don't need inside the stations, they will split randomly, but we take the whole stations out. And that's very important to avoid the overfitting, because I burn my, as I said, I burn my hands many times, and we even published this paper. This is back in 2014. There was this paper we published, and we published here a paper, and we said, oh, wow, if we take the whole stations out, or if we leave the stations, then it's a really different. So this was a modeling with a randomly subsetting. Imagine this is the same thing. So this is water content, same modeling, everything is the same, except here I take randomly subsetting, and here I take the whole stations out. It's a huge difference, right? So how come that random forest fits so perfectly, like R² was 0.96? I'm not sure, but I think it's because when you have the locations on the same locations, then the values are the values get locked in with that combination of features, and then the model always know what the values are. So it's very difficult, it has an extra help in predicting. Yes, and that's not realistic, because this thing, it only shows you what is the accuracy of that random forest at the stations. But we want to know what is the accuracy when you go anywhere in the space. Right? That's the real map accuracy. So if you go anywhere in the space, how accurate can you predict moisture? And this one only told us what is the accuracy at the stations. but nobody's interested in that. So then we computed this. Wow, this is a really huge difference. And I think this random forest cross validation, when we do taking the whole stations out, then it was similar to kriging. So it's a similar accuracy. It wasn't much better or much worse. It was similar. For soil temperature, it was a bit better than kriging, but for the soil moisture, water content was about similar. So that's very interesting visual explanation of the overfitting also. So that's what we do here, this blocking. And now we can go and train. We can go train this model. And now it's a bit computational. So I actually use this parallel package that by default it will fully parallelize. You see now it's using all the bars. These are called happy green bars, by the way. When you do programming, if you in R, more and more the good program is the one that you parallelize every step. Okay, so that's a good programming. Every step you can. So here's the green bars, and this is now modeling with a bit bigger data set. So this did take about maybe 5 seconds, right? And it's after the full parallelization. And now we have the model, and we see that the model looks good. We have the neural nets. We could exclude it, it's very low coefficient, so we could throw it out. But the other two, the GAMBoost and random forest, they help explain R² up to 0.87. And that's a good result, but the residual error, it's still relatively high, 2.9. So we get plus minus here, let me see. We predict plus minus 0.8 to plus 0.8 degrees, 2/3 of the point. So one standard deviation, it's a minus 1.8 to plus 1.8. So that's the errors we get for the daily temperatures. For anywhere, so this is let's say mapping accuracy with the blocking. So we assume this is anywhere in the space, this space we produced. So anywhere in this area. Okay, so that's the actual mapping accuracy. And then we can then do predictions. Let's do the variable importance first. Here's the variable. The variable importance code is a bit long. I don't have time to go to it. I wish it was just a single line. But you see that the LST nighttime, interestingly, looks like the MODIS nighttime images about 3 times more important than the daytime images for the daily temperature. So it's there's more variation, I think, in the nighttime images than in the daytime. And then we can do predictions. And predictions, I also do. I have to read. I have to subset. I want to predict for 4 days in August. Then I have to subset, and now I have to read it to R. But I don't read the whole year. I just read this August, let's say. So 1/12 of the images, I read it to R. And then I have to add some things. I have to, because I have the 8-day, I have the 8-day stack. I need to interpolate values between the 8 days in the MODIS space. And there's also a nice function I made for you that you can use universally. And that runs in parallel. Let me run that. So this one will take all the, so it creates like a space-time cube. And because I have only every 8 days, it will interpolate values of MODIS for every pixel. So you get these gradual changes. You understand? No, this time I just I have this approx function. And this time I just put it basically linear. But I could use in approx, I could use some spline or something, but then it's more computational. But you don't need anything. You just need a simple thing. And this one is really just to fill in these gaps. This one helps you fill in the gaps because look at this thing. If I have the gaps and if I do this approx, then if I have, like, for example, 3 missing values out of, let's say, 45 images, then it will fill in all the missing values. It's a very elegant way, and it's fully scalable. So you can apply to any type of data. It's a super simple gap filling. It fill gaps based on the temporal neighbors. It only looks at the temporal neighbors, not spatial neighbors. You could combine it with the, so what is the output that you get? I'll show you this. Output you get, so this is the, for example, we started with, I think 4 dates or something. And now we have for every day from 14 to 21, we have for every day, we know the MODIS temperature, and you can plot this and you will see it's kind of a linear model between the points. And we started with the, when you look at the X1 and X2, so this is the X1. This is what we started with. So you start with the 5th of August, 13th of August, 21st. That's what we started. And we finish with basically 8 days consistently, MODIS filled in, no missing values. Okay. And so now we prepare the prediction data, and now we can go and do predictions. And this is this thing. And how do we do predictions? We have to copy the data. Now I just copy because I don't save everything. Basically, I will subset the new data, new data, predict, then throw it away, then another day, and a day by day. So I have a prediction machine, but it doesn't create in RAM lots of things. So it just writes basically a geotiff. It will put a geotiff here, write GDAL, and then the geotiff pops up here in the as output. You get a geotiff, and so here are the predictions. So I already made them, so we don't have to remake them. And now we can look at the predictions. So this is, as I said, this is the MODIS original, missing values, artifacts, and here are the predictions. Predictions, we have no missing values except for the missing values in all images, and we don't have artifacts. Artifacts are minimized, and you see that the variation between days. You can see how the values change between days. And this is a result of space-time, now space-time machine learning for predictive mapping. Please close the door. And I can plot. Now I put 3 maps, but yeah, I didn't load this. I put only 3 maps, but I could put, for example, 8 maps and then plot them. I don't recommend it because it takes time. Even like plotting 3 maps, it takes 4 or 5 seconds. And then you get this thing. This one does have missing values. But it's possible because now I do, for the filtering, I only use 4 images. I should have used like maybe 2-month data and then filter all the missing values. Right. So there are some more missing values than I expected. But otherwise, you know, it looks, you can see that some days are warmer, some days a bit cooler, and locally you adjust and you make the predictions. So that was the daily meteo data set. So I think it's a very nice example. And then there is a Cook Farm data set. So the Cook Farm data set, it's in the landmap package. You can read about it if you want, but this is this space-time 3D plus time. So it's actually 4 dimensions. And I have the covariates and everything prepared. And this model is a bit longer. So I have also soil depth. So how deep you go in the soil. And I have some static covariates, and these are the dynamic covariates, the maximum temperature, minimum temperature. So I have the static dynamic. And then if I fit just a random forest, what happens is that I will overfit. And that's what happened exactly. This thing I'm just doing now, that's exactly what I used to do in this paper. So here, yes. So it's exactly now, I'm just repeating that. And I get the R square almost 0.9. Okay, so if I don't do any blocking, no ensemble, just random forest, I take the data as is. But if I do with the blocking, repeat that with the blocking. So now it's there's a blocking parameter. Repeat the modeling. Now the training is a bit also taking time. And you see it does what it does here. So this is the first learner. And you see it has 10 elements. So it means it fits 10 models. It does the 5-fold, it repeats 2 times. So it fits 10 elements just for the random forest. And then 10 elements for the superrunner machine, etc. And so that takes time. So now this is random forest is done. And then goes to the next learner, second learner, also running in parallel. And then the last learner, and then it fits finally the meta learner. And now we have the ensemble machine learning based on blocking also. And look at this now, R squared 0.4. So we go from 0.9 to 0.4, just because I put the blocking. And so obviously that's very important, because otherwise you get difference between this and this. Yes?
I have a question about random forest, because the idea with random forest is that you make, for example, the trees, that you split, the concept is that you split the data and then the random forest model itself makes its own new trees which are not observed. So with the blocking you avoid it.
No, you don't do any splitting. You just in this case I give all numeric target, numeric covariates, and then it fits many regression trees. Okay. And regression trees, they do the splitting. They are kind of optimized to minimize the RMSE, and then it makes an ensemble. That's the random forest. Random forest is also an ensemble, by the way, but it's based ensemble from one model.
Yeah, the idea that because with blocking, then the idea is that for example, not only part of the observation of all the, for example, one station in this case, then the normal method for it takes a part of the observation, for example, only night temperature and the other only day temperature and other both. But now you say, okay, you have to take all the observations, right? What's measured at that time at the station?
Yes, yeah. Yes. This you take everything, yeah. But with the blocking, I make sure. If I show you here in the article, maybe that will make it a bit clear. These are stations, right?
Yeah.
These are stations, and they go through depth. They have 4 depths.
Yeah.
And so what you have, not the triangles. Sorry, the triangles, not the dots. These are the stations, and basically. When you do now ensemble learning, you take the whole stations out. So you take maybe, I don't know, 1,000 measurements out, yeah. Then you model and it predicts that station. And then you get R squared 0.4, right? Because you took the whole stations out. So you don't overfit. I mean, this is obviously, it's not overfitting.
Yeah.
Whether this could be better, higher, I don't know. Probably no, I would say no. I think that's the realistic R squared. But the only way to know, it will be do probability sample and go and sample and do the same measurements through space-time, and then use the probability sample to validate how good it is. But most likely it will be about this number. And then we make the predictions. Again, I have to prepare the new data. I call it new ST. And then I do predictions, and off we go. Here's the map. And I predicted only one depth, and I put it like this. So you see the station data, and you see the predicted values. And you see where the hot spots, where the soil is a bit drier, etc. I could also just plot this. Maybe I will plot this just to show you. Just in Google Earth, I can do KML. Any more questions? No? Color scale. Yes, please.
So, we're talking about Ensemble. It's something way beyond than boosting and bagging, right? Boosting and bagging is only related to decision trees and reports, whereas Ensemble you can actually combine things. Different techniques.
The ensemble is the general name, right? That's the general name. But the algorithm to make the final predictions, that's what the differs.
Yeah.
So if you look at what I said here, if I look at Stack Learner, so there are different ways you can do average. That's a very simple. That's computational for sure, the easiest. Average also assumes that all the learners have the same weight, which we saw it's not the case. So that will be making a damage, right? Then you can do stacking, no CV, no cross-validation. You can do stacking with cross-validation. That's the most computational. And if you do it like a 5-fold, it means you have to fit 10 times model per learner. So then it's about, yeah, you fit about 10 times more models, way more training. And then you have this hill climb and you have the compress. And then compress is to use a neural net to compress the model from 4 learners, I don't know, to 1. Yes, so these are the options in MLR. H2O has something else. But I always use, almost exclusively, I use the stack CV because I want to do blocking. Because blocking very important. So let me plot this. I plot this. Oh yeah, I did plot it already. I just have to open it. Did somebody figure out how to reset the Google Earth? So here's the Windows 10. Now I'm passing to my Windows, and let's take a look at this data set we computed. Now we jump to another. So here's the soil moisture. What I open it here so you can look. Let's take a look. So have to turn this off. So as you see, this is the red is the higher soil moisture, and the blue is the lower. So what happened is basically we see looks like here there's like I think it's connected with the soil texture. But you can see that the soil moisture depends on the place. Yes. So you can see where it's obviously here it's a little like a valley. Do you see this? It's like a little valley, and here we have a bit higher. There's accumulation of soil moisture, but it's also here there's higher. So yeah, it's interesting. And now I could go and predict basically now how many maps could I make. Now imagine how many maps if I have 365 days, 4 depths. So that's 4 times 365 just for 1 year, just for one variable. And I have 3 variables. And if I want to map them all, and then I have also uncertainty, so I can make a 10,000 maps. And with this thing, I'm done with the 2 first case studies, and now I will pass it on to my colleague, Carmelo, and he's going to now show you a third example, which is with our project, European project. These are just like school examples, and now this is a real example. So let me pass on to you the microphone.
Work. Let's see. Not the sound. It's okay. Perfect. So what we are going to see here, it's a case of species distribution modeling, which for who's not familiar with it, I can have some kind of a gentle introduction to the problem here with the slides. So we will talk about correlative species distribution models, which basically try to associate values of predictor variables in both environmental and feature space to the location of the species that were actually observed. And then we use different models to actually estimate the similarity between these sites and produce two kind of results. Either, as you can see in this slide, maps that show like a 0-1 distribution of the maps, so areas where the species could occur and areas where the species does not occur, or probability maps. So we have a gradient that goes from 0 to 100% of where the species could possibly be present. So based on this, we just say that the probability of occurrence, or the 0-1 of one species, is just a function of different predictor variables that in our case could be both climate, terrain, spectral reflections, and also the competition between different species, so interspecific competition that is usually not included into the species distribution models because it's very difficult to actually assess that. So what we are now using for these four kind of groups of variables, we use temperature, precipitation, snow cover, and other kind of environmental factors that we gather always from remotely sensed data, or DTM, slope, pedology, and all these kind of things. From spectral reflectance, we just use Landsat data because we are trying to model on a time period that goes from 2000 to 2020. So data sets that come from Sentinel, for example, are not available, so back in time. And then the competition that we use is species distribution maps for species that are not the species target that we are actually mapping. So for example, we are focused on forestry species here. So there is a big data set of distribution maps that come from the JRC, the European Forest Atlas. And we use these maps to model the presence of other species in the same environment for the target species that we are trying to model. So based on that, we can say, okay, modeling is easy. We just take the data, we plug it into a model, and we get a response. But as Tom already mentioned today, we have to understand first the data. It's not so easy. So in this case, in species distribution modeling, for example, we have to assess if we are using just as an input data set a presence only dataset, so where we have just a dataset with rows that record where the species that we are actually trying to target is located, or if we have more hybrid dataset, so with both zeros, so where the species is not located, is not observed, and presence, so ones, where the species is actually located. And in this case, we have to actually check if there are, for example, missing values in the covariates that we are trying to use for modeling, if there are very skewed distribution, if the data set between presence and Nansen data is very unbalanced, that would actually influence the prediction of the models. Then we also have to understand the problem. So are we trying to model the suitability of a certain area, or are we trying to model the realized niche where the species is actually located, which is different to just assess where the species could potentially be present. So in Europe, we have previous distribution maps that are not very precise, that are very low resolution, and they do not record a very high probability for the species because it's very difficult to model these kind of things. And we have different either European or pan-European datasets available that record either just the presence or also the absence of certain species. And for example, this document that was published by the JRC in 2020 gives an overview of both the dataset that can be used to model the forestry species and also the products that are already available, the state-of-the-art products that are already available to show where the species that we're trying to model are located, which are the same maps that I was showing here for the species that we are trying to model. So the dataset that we are using are just the UNFI dataset and GBIF dataset, which are both the mostly density in terms of density of points, and also they cover a very long time span that matches the time span that we are trying to cover with our models. While the other data sets, even if they are useful or important, they are either ancillary or they have a very coarse resolution, and the sampling that was used to actually gather the occurrence of the points is at a very coarse resolution, like 1 point every 20 kilometers. So it's very difficult to assess if this data can be used to produce very high resolution maps, like at 120 meters or 30 meters or more. So we are now using as base for our models this harmonized 3-species dataset that was produced by Johannes Heisig last year during the last summer school recorded by OpenGeoHub in 2020. And you can find this GitLab repository where you can download the code that is used to produce this dataset, that basically tries to harmonize the European forest inventory dataset, the GBAF dataset, and also points that come from the Lucas project from Copernicus, that it's a project based on mainly on gathering ground truth observation across all Europe for land cover data. And among these points, we can actually find also points that are related to trees.
How many points in total?
In total, it's 3.8 million of points of trees. And this is just the raw data set with all the observations. So you can find different kind of metadata inside the data set. So for example, aside from classical metadata like the coordinates of where the point is located and the species, you can find from which data set it was downloaded. In this case, this point comes from the GBIF data set, and also the location accuracy of the points. Usually points that come from the Lucas dataset have an accuracy of 0 meters because you actually have the picture of the tree that is actually sampled or surveyed, while instead for GBIF, you can have points that have a very high uncertainty in terms of location. It can be even 5 kilometers. So it's very difficult to model high resolution maps with these kind of data sets. And that's one of the main points of this of my talk. It's like you have to clean your data set and you check if the points that you are using can be used, because GBIF is also global. It's not just covering Europe, and is one of the main data sets that is usually used for species distribution modeling. So we can now have a look at how the points are located in space. You can see how many points we have per country and how the points are located. This is a kernel density map that's produced on a 10-kilometer grid. So you can see that even if, for example, Spain has a lot of points, they're actually clustered in this part, which are mostly plantations of olive trees and cork oaks. Or, for example, here in Belgium is one of the mostly high density country where you actually have every kilometer you have a tree that is actually regularly sampled. And then you may have like problems in the Eastern European countries where you don't have actually points. You have very, very few occurrences, and the whole country is not even completely covered. So how can we actually try to remove or handle this bias into the dataset? What we did is using land cover classification maps to be produced for Europe for 20 years. And we created forest masks, and we overlaid all the points that we have that have also a target about time. So each point is sampled in a specific year. And we extracted the values of the probability of land cover classes for the whole 20 years. And we just took all the points that were covering like either coniferous forests or broadleaf forests or other kind of vegetation, so that we know that for the whole time period that we were covering from 2000 to 2020, we were sure that these points were forests or at least trees. After that, we cleaned the whole data set, and that's what we ended up with. We just have a small data set with almost the same amount of points for every species, plus absence data that comes from the Lucas dataset that I was mentioning. And the only data that you have in terms of metadata is just like the year of the point, if this point comes from observation or from this kind of procedure that we were talking about here, and the species that we are actually trying to target. The tile ID is, of course, like we divided the whole Europe in a grid of 30 kilometers that are among like 7,000 or more tiles covered in points. So this is actually the column that we will use for blocking during the Ensemble machine learning model.
So here we don't have the stations, but we still want to block because we had this clustering problem, the one that Hengl And so we pick up arbitrarily 30 kilometer. But if you take more kilometer distance, then you degrade the model. But if you take too little distance, then you might be overfitting because of the clustering. That's why we pick up this blocking by the spatial block.
This is the amount of covariates in total that we will use in your dataset. They are already filtered by a feature selection process, so there are just 180 instead of all these 600 that we can see here. And they are divided in the 4 groups that I was mentioning. So either climate covariates, terrain covariates, reflectance covariates, and competition that comes from already other suitability maps for the other species. To have an idea that what we use, for example, we have a long-term average from climate and temperature that comes from the bioclim dataset that was produced from observations that come from meteorological stations that go be like around the 70s. And then you have a long-term average that is computed from the 70s to 2013. So in that way, we can have an estimate of the average conditions of the climate for the species. And then we also have a time series of different climatic variables, like the air temperature, the precipitation, and the surface temperature. That was computed by the Copernicus project from the ERA5 dataset. And this is actually 1 kilometer daily observations of different variables that we aggregated by month. And for each value aggregated by month, we took 3 different parameters: the monthly average, the sum for the precipitation, and the sum of the previous 5 years. We have both a long term from bioclim, a short term based on a 5 years time window from this, and also monthly values. And these are all, this data set was resampled by us and is available in the Open Data Science viewer that Tom already showed. Then from terrain, we use, for example, a proxy from continentality based on a distance from the coastline, different derivatives from a digital DTM at high resolution for the whole Europe, available at different resolution on the data portal, and also reflectance data from Landsat. This is different from the Landsat data that you can, for example, download for Earth Explorer, or it is available on Google Earth Engine, because it's actually reprocessed by the University of Maryland to be consistent across all the 3 Landsat satellites that we normally use, like Landsat 4, 5, 7, and 8. And what we did was to download this whole data set, create 4 different composites per year. So we have 4 seasons: winter, spring, summer, and fall. From these, we removed cloud and cloud shadows using the data that already the University of Maryland provides. And then we computed for each image, each composite, 3 different interquantiles to see the distribution of the pixels in the environmental space. Then we mosaicked everything, and we use a temporal moving window to gap fill the data. And that's what we get for the different quantiles in the distribution of the pixel for each year and each season. So at the end of the day,
understand this, the quantiles, like reflectances over a longer period, you can extract distribution. And if you take the 25% quantile, that's a low reflectances, median, and high reflectances. And every season has a different. And so basically from one variable, which is the Landsat reflectance, we derive 3 variables. But because we aggregate it through time. Yes, and we do it so we can fill in the gaps and we have something smoother.
yes.
Just daily.
So you can see, for example, that in this mosaic that is from fall 2019, even if we aggregated all the pictures that come from the RGB bands for Europe, there are a lot of gaps, and we gap filled that based on a temporal moving window when we computed all these distributions. So at the end of the day, even if we have for 1 pixel that, for example, was surveyed in 2006, we have just like 91 covariates that come from the different Landsat bands, plus the 3 quantiles, plus the 4 season. Instead, we have points that are observed across 20 years. So in total, we have more than almost 2,000 of reflectance covariates for the whole time series. So having an idea of how the dataset is built, then we skip the hyperparameter optimization and the feature selection for the sake of time in the model. And we can go back.
And one image Landsat called Europe 30 meters, it's about 2 gig or something.
Yes, something like that.
We have 1,000
For one band.
1,800, and one is 2 gig. So you get the idea. It's a big data.
It's a lot of data. So let's go back here. Here we're actually facing, as I was mentioning, this is at 0, 1 with a probability distribution. It's not anymore a regression problem, but it's a classification problem. So if you want to follow from the markdown, this is the distribution of the points that we are using with the occurrence of the data. And you can see them also in QGIS. So this is the distribution of the points. It takes a while to render. All the green points that you can see is the absence data that comes from the Lucas points, while all the blue points are actually where the species was actually recorded. And you can also check visually if this species is actually there by also adding the street view coverage from Google, and then clicking on one of the presence points to look at the street view and see if the species that was actually surveyed was the species that we were looking for. Let's see this, that's very close to the street, for example. There is also another plugin that you can use integrated in QGIS, and you can have in QGIS a small window on the left where you can see the trees.
You jump and you validate the point.
So you can check, okay, this species is the one that we were looking for.
Yeah,
so the point is correct.
We didn't, of course, check all the points. But
yeah,
students or somebody, we would have given them and even do fixes. So therefore, I told you the machine learning, lots of data cleaning, lots of preparation, checking.
Yep.
It's come from Lucas, right? Not from the biodiversity inventory.
Yeah, I can come from either Lucas, the GBIF, or from National Forest Inventory. So we have also the plots from the forest inventories from the different countries in Europe. So it depends. You can check from the original dataset from which one this point comes from.
When it comes to other species, like dynamic species, it's another approach.
Yeah, I mean, of course, like if they are like species that do not move, it's easy to do this in this way. So let's go back to the markdown. Where was it?
The next one, the next.
Yeah, that's it. So we see where the trees are located, and what we are using is just like, okay, let's see how the data set look like. How many covariates do we have? As I said, we already filtered the covariates, and we have around 180 for this model. So let's go back here in the model. You can see how the data set looks like. Also, it's the same. These are the same fields that you could have seen in QGIS. And then we can check. This is the function that Tom prepared that fits Spatiotemporal Ensemble machine learning model. In this case, we are using random forest. The ranger is the name of the parallelized version of the algorithm in R. XGBoost or extreme gradient boost. So we are using already bugging with random forest, boosting with XGBoost, and then we are also fitting a generalized linear model. And then by training the model, which is very fast because your dataset is already clean and is also not very big, we can get both the feature importance. Here, the image was not loaded, I think. Yeah, was not already loaded. So let's load this. Also, this is read in parallel because the data table reads everything in parallel. These are the fields that I was talking about. Then we have here, this is plotting all the points, and then we have everything here. Yes. There we are.
Mr. Hengl, you can open the progress bar.
I think it's already done.
Oh, okay.
So it was really fast.
I subset to 5%.
Yeah, the whole dataset is more than 700,000 points for this species, I think. Because for every species, we have different occurrences of points. So the imbalance in the dataset is always different.
And the distribution through time, is it, there are some years we have more data, some
Yeah.
years less data?
Yeah.
So there's peaks in the time. So there's problems with this data. So
it's difficult. Also, you can see here from this is the meta learner. As a meta learner in this model, we are using logistic regression because we want to constrain all the predictions that we get from the previous models in an interval that goes from 0 to 1. And then if we actually wanted to model just a binary classification, usually the threshold, the default value of threshold is 0.5. So every prediction that goes below 0.5 is classified as 0, and every prediction above it's classified as 1. But here we are not trying to assess that. We are trying to make probabilities. So we get the straight values that go from 0 to 100. And as you can see here from the output of the model, XGBoost is actually the model that is not useful for this task. Problem is that XGBoost is also a kind of algorithm that's very sensible to fine-tuning, and we skipped fine-tuning here. So what we actually found during the training of our models is that if you spend time to fine-tune this algorithm, it actually turns quite useful. And from the slides, let's go back here. I got them open here, yes. This is, for example, what we do when we predict for the tile that I gave as an example for the different three algorithms that are using as base learners. So as I said, XGBoost doesn't turn out to be very sensible. You see that the values are very smoothed. But here instead, random forest and GLM perform quite well. And what then the meta learner does is using as an input data set, a data frame, that has the same amount of observations that we use for training with all the points. Then we use blocking with the tile ID that I mentioned before. And then we use the predicted value for every single algorithm to generate a final prediction, which is used by the stacking method that's Tom described before to get the final tile. And this is, for example, the output of the model for 2015 with probability values that go from 0 to 100, and you can see that all the low values are actually values where you can see either a lake or a city or a street, while the high values are where the mountains and the forests are. So it actually performs quite well. Usually you would use the area under the curve to assess the validity of your model. And as Tom already mentioned, we can use Ensemble machine learning for different kind of tasks. And we have usually the same step-to-step process depending on how complex the task is. But once you learn how to do it, and once you learn what your data is telling to you, it's not difficult to actually model what is the task that you're looking for. So if you have,
can you put that as a prediction? I think I have it saved.
Yeah, you have another one that's that can see where you can see the differences, across the years, because we are using covariates in the dataset that are static, so they are the same values for the whole 20 years, and instead time series of, for example, climatic data that are different across the different years.
So where is the difference here? Let's see.
You can see, for example, here,
this one here.
here you can see that there is an increase in forest cover in this part, and it's around the roads. And then also here, there's some fragmentation instead. And you can see that the values are, like the difference is very high. We go from values that are around 0 to 20 to values that are from 60 to 80. So of course, you have all these maps are also correlated with maps that show the uncertainty of the model. So you can see that even if you have a big change here, it might be an error of the model, because all the three models are maybe predicting not correctly there. So you have a very high uncertainty. So you say, okay, this area I will not use as a valid value. But in other areas where you have very low value of uncertainty, you can see, okay, the model is telling me that there is something wrong here. There's a change, for example. So any question?
Many?
Maybe for the coffee break.
Let's do. We have 5 more minutes for questions.
Let's see if there is something in the chat. Okay, let's see. I know this is, these are old. I think these are more for you. No, these are recent. This one, for example, can we apply a mask to ignore some areas?
Well, the best way to do this blocking is to do it systematically, right? Like we do the spatial blocking.
Yeah, of course, you can apply a mask to ignore some areas.
Blocking by station, so you have to do it systematically. You cannot play with it. I mean, that wouldn't be objective. So you need to allow randomization and do it very systematically.
For example, you can see here for the people that are asking for a mask, that there are values that are completely white. This is because we used a mask to avoid predicting in areas that are covered by water, for example. That's the same that we are doing, for example, where the sea is and anything. So you can do the same for the mask that you would create with your JEDI data to avoid predicting in those areas.
We have this map for now 15 species.
15 species, yes.
We want to do 60. It was a lot of computing, actually. We stopped with 15. But we have a capacity to do all 60 species. Space time 20 years, but we switched from 30 meters to 120 meters, so 16 times less data volume, because otherwise it was too much.
And also we're predicting different things.
Hengl will show these maps on Thursday, I think.
Yeah, Thursday morning.
We will give a demo. They will be in the app, so it's a launch. So we have it's actually a celebration that after 6 months, I think.
Yeah, more.
We have it. So that's great, and we want to get countries to give us small point data, and we think we could train a full forestry species model, so that we know exactly which are the key drivers, which is the key covariates that help with the mapping accuracy, and that we can then also support all the forestry projects, all the land restoration, reforestation projects. So we like to really provide the data openly, so there's a support. And we will have two predictions. One is the actual distribution. This was all actual distribution.
Yeah, this is realized distribution of the species. That's why we use reflectance data, because otherwise.
The potential predictions, and this will be visible in the
slider.
You will have this split, and you will be able to open, let's say, somewhere in Germany, and you say this is the actual Fargus Latica, this is where it could happen.
Yeah.
Potential just based on the code.
And the difference in the two could be because either there you have a city, so the species cannot physically grow there, or because there is a problem with dissemination, or like with the moving of the species in particular areas.
So I think we can stop now. Thank you,
Yeah.
Bonannella. I'll take over. I'll just
Sure.
finish the session.
There you go.
So you saw the three case studies. They are nicely picked, I think. You notice there's different problems. All three are a bit maybe complex, but this is they reflect the type of data you use in real life. So especially the last one is actually, inside the project, but we are able to take something which is like complex, and we're able to put it in the R Markdown. So we really work hard to simplify that, so it can be run within basically within less than 1 minute. And you see also very nice about MLR is that you can have the classification problem, but as a meta learner, you use a regression. So you combine classification and regression. When you work on the 0-1 states, it's kind of both classification and regression very similar. When you have a multi-state variables, then it's a bit different. Then it's not easy to combine. But here it worked very well, and we also have for every pixel we have uncertainty, which usually people don't do in the species distribution models, right? Carmelo, they don't do it, so we map actually. Yes. Yeah, so we map for every pixel, we map the uncertainty. I would like to switch to MLR3. I didn't mention that, maybe they're just for the end. As you see, lots of code is running MLR, but if you go to the MLR website, they tell you don't use it. So don't get confused. They said this project is retired. You see, these people automated, and you see, that's what I told you. You automate in machine learning, and then you retire. So it says this project retired. So they said, don't use it, go to MLR3. But it's not simple MLR3. It's the lots of changes MLR3, so it's a different. It uses R6 for data, which is different class. It's more object-based programming. The command names are completely changed. Also, the logic how you model. Also, it's split in multiple packages and complexity. And I cannot start using it. So it looks like it's too steep now. The curve is too steep. So I'm hoping to speak with Patrick next days, and he shows me that, because you are you do the development for an MLR3, right? So you show me some tricks, because we would like to get it translate lots of code, you know. But I just at the moment I don't know how to, like this blocking, how to set it up. So that's the MLR3. MLR3 won some awards, I heard. So it's a really vital project, and I do see that it's running faster in this object-based programming. It looks more and more like a Python, I think. Yeah, it's great that also community grew. I think it's more people now. There's also a package to do spatiotemporal learning, right? How's it called? Okay, great. But that's the future. Now we do, as I said, this all works. The code is fine. The MLR package is still running. It will run, you know, maybe a couple of years more. But then if somebody changes, and they might break, and then it just goes off crown, and then you have to fix it yourself. But for now, it does work. You can do, and everything we do, it's parallelized. So there's nothing inefficient with this. But of course, it will be better to switch to MLR3. Yes. So with this thing, I will now stop. Let me see if there's more Q&As. Chat, no. And then also the Mattermost, RDev, I didn't see any much questions. You can keep on asking people that are online. Please keep on asking questions to Mattermost. Just use the RDev group, and if something is interesting, I can answer also tonight. Not a problem, but please keep on using